All right, welcome back. We are picking up where we left off on error correction codes. Over the weekend, I asked you to watch a pair of videos on hamming error correction codes. And thank you all for participating by posting your comments, critiques, and questions onto Piazza. I will peruse them this afternoon and give you credit and answer your questions where I can. I just got an email saying that next quarter the 526 offering is under-enrolled, so I will repeat my pitch that if you're interested in taking what we've learned in this class and taking the next step, I encourage you all, everyone who's in this class, I would have no problem, regardless of your undergraduate or graduate standing, taking you in 526. I think that it would be a shame to take this class and then not take the sequel, is basically what I'm trying to say. But I understand everyone has their priorities. My priorities are to get you to take 526. So there you have it. Any questions before I launch back into lecture?
Oh, I procrastinate that. I will send you one this afternoon.
Okay, yeah, I was also surprised that the you've got low enrollment email came so quick. Like it seems like people are still registering, but I guess graduate students and then seniors, like the registration goes in that order. So they would have expected the people who are going to take the class to have registered already. But yeah, so get back to me sooner rather than later on that,
Awesome.
please. Okay, so let's go over to the PowerPoint. This is super tiny. Let's make that a bit bigger. Okay, we left off on Friday with hamming 7.4, and then you looked at a slightly larger hamming explanation on the YouTube videos. And I think, so we actually covered this already, where in this particular version of this diagram, we're not talking about what's called a systematic code necessarily. So as a quick vocab lesson, a systematic code is exactly what we had in the picture before. It's what happens when you have your code word is comprised of just gluing on the check sequence. So your data and your frame check sequence appear as separate chunks that are just glued together, and that this entire thing becomes the code word. So the implementation of hamming 7.4 that we saw, and the one that you saw on your YouTube video, was a non-systematic code because the code word had the frame check sequence, or the check bits, kind of sprinkled in at positions that were powers of 2. So just to show you, like, there's nothing necessarily good or bad about a systematic or non-systematic code. That's just classifications. And so in this particular diagram, we don't have this kind of glue-on bit. We were saying the code word can be comprised of both data bits and check bits wherever. And then we've also talked about false negatives and false positives, is that we can have all of the above in the receiver end. We'd like to have no error, and then for our error correction code to tell us that we have no error. But it is also unavoidable that if just the wrong bits get flipped and one code word gets flipped into another code word, then think about what your receiver will see. Your receiver will see a code word come in, and it will look that up, and it will say, oh, I know the data word corresponding to this code word. You have to say that is the correct thing to do, right? So imagine what happens if we transmit code word 1, and one of two things happen. In situation 1, code word 1 comes through perfectly. Our error correction detection says, oh, no errors. And therefore, in a lookup table, it'll spit out the data word corresponding to that code word. Okay, that's what you would want to have happen, because if nothing bad happens, there's something for your error correction to do. In scenario 2, code word 1 could potentially be flipped, like just the right/wrong bits could be flipped, so that what is received is actually another valid code word, but not the one you sent. Now, from your receiver's perspective, your receiver can't see anywhere above this line. And so your receiver says, oh, look, code word number 2. I have to conclude no error. Therefore, I'm going to output data word number 2. Okay, so this is my selling point, is that if you have a code word that gets flipped into another code word, your error correction code can't possibly correct for that, because it would mean that sometimes your receiver sees a valid code word and thinks this is fishy. But it's unreasonable to expect it to do that, because if it sees a valid code word, it should want that to be decodable instantaneously, the no error situation. So you will always have a non-zero probability of a false negative. Okay, and this is an example of why. Now, the likelihood of code word 1 being flipped into code word 2 gets smaller the larger your code word space is. Right? The further the Hamming distance is between code words, we define the Hamming distance to be the number of bits that have to be flipped to change one code word into another. So if you can increase that distance, that means you increase the number of bits that have to be flipped. And if each of those bits getting flipped is a small probability, then they compound, they multiply. And so you get an even smaller and smaller probability. Okay, so that's the selling point for making your code word space large. The trade-off for that, of course, is making your code word space large relative to your data word space means you are sending more check bits than data bits in some senses, right? So that we say that the rate of the code goes down if, remember, the rate was the ratio of data bits to total bits. And so if we increase n while keeping k constant, then the rate goes down. And so that means you're sending more bits but getting less data per bit, if you like. Okay. Questions so far? This is kind of a rehash. So we've talked about Hamming codes. There are all these classes of different kinds of codes. And the first kind of, we just kind of throw Hamming at you, but you can talk about large classes of codes with these, how we talked about linear systems and nonlinear systems. So let's talk about linear codes, and in this case, linear block codes. And it's just the idea that your code words can be generated by linear algebra. So we can do matrix algebra to change data words into code words. And so this is that exact operation. So this is data word D, and we're gonna treat them as row vectors, which is a little strange when you talk about linear algebra. It's kind of more common to talk about column vectors. But because we write our binary sequences left to right or right to left instead of top to bottom, it makes some sense to talk about these as row vectors. But the big G here is a matrix, which will have to be, if D is 1 by k, then G will have to be k by n to produce a code word that is then 1 by n. Okay, so G is going to be a k by n matrix that takes the data word vector D and maps it to a code word vector C. And all we've got here is the notion that G1 comma I would be the first column of G. And then G2 comma I would be the second column. Yeah, I think that's what I want to say. And then, of course, because we're in these binary vector spaces, all of the vector addition needs to be done bitwise XOR. So that's what I'm meaning here. These are XOR operations. And then we can get back to that definition of a systematic code is if you can partition your G matrix, the matrix that maps data words to code words, if you can partition it as having an identity on the left, if you like, and then something else on the right. Because what would this mean when you go to do D times G? Well, that's D times identity and another matrix P. But that would be a vector that was D times identity, comma, D times P. And so D times identity would just be D. And then your frame check sequence would be the data word times the P part of your generator matrix. So this is what makes the code systematic, is if the data word appears uncorrupted first, and then the frame check sequence is then glued onto that. Let's see here. Okay, so let's give this a go. We have got a G matrix that is 3 by 6. So this is our first example, actually. Well, we did an example last lecture. And at our transmit, so this slide is divided left and right. On the left would be our transmit location. We've got an identity matrix, and then we've got this P, which some people call the parity check matrix, submatrix of G. And so what can we learn from, if I just give you G? Well, the number of rows is K. So that means we have a data word space with 2 to the 3, 2 to the K vectors. And here they all here they are all spelled out from 0 to 7. And then the number of columns tells us that we are going to inflate. This is a rate 1/2 code, so 3 over 6. And so, yeah, all we're going to say is that anytime you want to send a data word, which again is your incoming bit stream, but just chunked in terms of 3 bits at a time, then you're going to take that data word, you're going to left multiply it onto G, and the result, well, you're going to actually take the data word and you're going to left multiply it onto P, because that would save you time, because then you're not doing a 3 by 6 matrix, you're doing a 3 by 3 transformation, because we have guaranteed a systematic code. We can just take D and say plop it right there, and then do a smaller matrix multiplication and concatenate it on the end. Any questions on generating the code word using a matrix here? So on the receive side, we haven't talked about how to. Well, I mean, should we build out the code words? Yeah, let's do an example. Let's see what happens for if the data word is 111. So again, I would write that up here. And we know the first 3 elements of this code word are going to be the data word because it's systematic. So all I want to do now is do the D times P. So here I'm going to do this row times this column, which is 1 times 1, which is 1, 0 times 1, which is 0, and 1 times 1. So I'm XORing 1 with 0 with 1. And I think I get false out of all that. So again, to do that out explicitly, I'm taking 1 times 1, XOR 1 times 0, XOR 1 times 1. Okay, so 1 XOR false XOR true. And right, this is XOR, bitwise XOR is like addition in that you can do it in whatever order. In particular, if I have two ones here, then I know that my XOR is going to result in false. And so that I know that all of my XORs are going to be false. So that's where I got this 0. Okay, so if I keep doing that with the next column in P, I'm going to get 0 XOR 1 XOR 1, which is another 0. And then I'm going to get, in the third column of P, 1 XOR 1 XOR 0, which is another 0. Okay, so that's how we can take the data word 111 and map it to a code word 1110000. Sorry, 000, 3 zeros. And when I do this in real life, in face-to-face, I then allocate one other data word to every student in the class. I don't know if that will work today, because then I would have you come up and write it on the board. So let me instead, let me just do another example, and then you can fill in the gaps. So let's try. Let's try sending this data word. So 010. Okay, so we know it's systematic, so we can just copy the first 3 bits. And now we'll do 1 times 0, 0, 0 times 1, 0, 1 times 0, 0. And XORs of all those zeros is going to give me a 0. So now we've got, I'll do the fifth element here is 0 times 0 XOR 1 times 1 XOR 0 times 1. Okay, so I think we get 0 XOR 1 XOR 0. And this is our first non-zero check bit. So we get a 1 there. Okay, this is fun, right? And let's do one more. So I get 0 XOR 1 XOR 0. So I get a 1 there. Okay. So this is mostly just to show you that you don't always get zeros as your check bits with this code. And so what you would do is you could, at your receiver, you would say, okay, look, we've got 8 code words, and those map to these particular data words. So if you ever see this code word, bang, you can just use lookup table and get your data word and pass it on. Or even better, because it's systematic, you can say, oh, if I ever see this on my receiver, chop off the right-hand half and then pass this along. Right? That's one of the advantages of systematic codes. You don't actually have to do any math to get the data word out of it. But the more interesting part, like the reason that we use error correcting codes is not when nothing goes wrong, it's to correct for when something goes wrong. So let's say that we end up receiving this string, and it is not one of our code words in our lookup table. So what we've got to do is introduce this notion of what's called a parity check matrix. And the way to construct it is as soon as you have your generator matrix is what this one is called. Generator. Then you can partition it into the identity matrix and the P matrix, and then to build your parity check matrix, you take P transpose and you concatenate it with your identity matrix again. Okay, so this is P transpose, and this is, if you like, it's I transpose, but that's the same thing as identity. Okay, so what you're going to do is you're going to build what's called the syndrome. And I have no idea why that word got chosen for this thing. But the syndrome is defined as the sequence, the bit string, formed when multiplying the received bit string by your parity check matrix transpose. Okay. So in this case, we have got this received bit string, and when you left multiply it onto H transpose, you are going to get out a syndrome that is 1, 1, 0. And then you are looking for the code word who's closest to this syndrome, if you like. So what we need to do is we need to find E, which is, again, the error. We need to find the E that takes R and brings it to the closest valid code word. So we need to find this error. And the way to do that is find it as the inverse of this linear operation. It is the bit string that when you multiply by H transpose gets you your syndrome. Okay. So to make this concrete, there are actually two error vectors that make this true. The E vector that is 0, 0, 1, 0, 0, when you multiply by H transpose, you get this syndrome that we got from before. But so do these other possible error vectors. Okay, so if I propose this to you and I say, okay, the possible error vectors that we could have in this transmission are these three, which one is most likely to have happened?
I'm debating between the second last one to the last one. The last one doesn't have any. Well,
So remember, an error vector is a metric of how many bits were flipped, right? If we look at the weight of an error vector, that represents how many, like the quantity of bits that were flipped.
oh yeah. So it'd
So
probably be the first one, right?
it's got to be the first one. Yeah.
Yeah.
Yeah. When you said you're debating between the last two, I was like, oh no.
Yeah, that I may have had it flipped.
Yeah. So this, they're all
Yeah, I
possible.
guess.
So I don't want to get, I don't want to get the idea that the others are impossible to have happened, but this is, in some sense, the maximum likelihood, right? The probability of this error vector occurring is higher than the probability of either of the other two, because either of the other two require more than one bit to be flipped, and the probability of multiple bits being flipped is the probability of a single bit being flipped to that power in a binary symmetric channel. Okay, so once we've settled on the maximum likelihood error vector, then we're able to compute the maximum likelihood code word as the XOR between R and this error vector. So we can do that by saying we take the first two elements of R, and then we're going to XOR this one with this one, so we get 1, and then 0, 1, 1, because we're XORing with 0. And because this is a systematic code, we then get to say, okay, this is our most likely data word. Okay, it is the data word that produces the code word that is closest in a Hamming distance to our received code word, which is, again, a maximum likelihood measurement. Questions on this?
I had a question about your parity check matrix.
Mhm.
That's right side, you said that's the identity matrix, but why is the bottom right bit still a 0?
Because I have a typo. Yeah, good catch.
I just have a quick question. So you pick that the first error matrix because that one, when you XOR it with R, causes the least bit flips. Is that why? Is the max likelihood?
Exactly. So
Okay.
the error vector, wherever there's a 1 in the error vector, that represents an error in that bit placement. And so the error vector with the least ones represents the least bit flips, which represents the most likely event.
Okay. Thank you.
Yeah. Okay. Any other questions on this? I'm glad you're following close enough to find the typos. I appreciate that. Okay, so I am going to go a little bit off script again because we need to know a little bit about cyclic codes before we can get to cyclic redundancy checks. So forgive me while I interject a blank slide here. Okay, so let's talk a moment. Let's have an aside to talk about cyclic codes. And if you want to place this in the realm of stuff that we've talked about already, cyclic codes are a subset of linear block codes. So every cyclic code can be formed by that kind of matrix operation that I was telling you about earlier. But not all linear block codes are cyclic codes. So the Venn diagram is wholly inclusive. And what makes a cyclic code cyclic is that if C, the vector C, which has a bunch of bits in it, so call them C1, C2, C3, up to Cn, if this is a valid code word, then every cyclic permutation of this would also be a valid code word. That means that C2, C3, Cn, C1 is also a valid code word. And just to remind you, I'm using the term valid code word to mean a code word that one of your data words gets mapped to. And this continues like all the way. So ... in both directions. So now Cn, comma C1, comma C2 to Cn minus 1 is also a valid code word. Okay, and we can see that actually if you're done copying that, I'm going to go back to the previous slide for a moment. That this is not a cyclic code because this code word down here is not a cyclic permutation of this code word up here. Okay. So just to give you an example, an anti-example. So all I'm saying is that what we're doing is we're taking the concept of replacing data words with code words with an extra rule, is that whatever your mapping that you choose, it has to map data words to cyclic permutations of a fixed binary sequence. Okay. And then just for notation's sake, if the vector C is defined as the bits C1, C2, C3 up to Cn, then I'm going to call the vector C permuted by one left shift as this guy. So C with the superscript of parenthesis 1 means the vector C left shifted by 1, which means that this would be known as the vector C left shifted by n spaces. Okay, and again, these left shifts are all understood to be circular shifts. And let me just give you a preview of why anyone would want to do this. It seems like, why, like, so who cares? It's just a special, but think about if you have only one string of bits that you're trying to map your data, your received bits to, and instead of like a list of different strings, your list of strings is a cyclic permutation of your one string. That's significantly less memory that you need at your receiver. Right, you really only need to remember n bits in the correct order, and then you can, instead of storing 2 to the k different code words, you can store one code word and then shift it and do all your checks against a shifted version rather than 2 to the k independent random strings of bits. So there are memory savings right off the bat. Okay, so what this also allows us to do is to talk about cyclic codes not as a vector, and I know I've been all about vectors in this class, but we can think about them as polynomials as well. And yeah, it's true that polynomials are also vectors in the space of polynomials, but this is going to be a powerful tool. So you can think of a cyclic code not just as a string of bits, but as a polynomial. That is, the polynomial c of x, so, and x is just whatever, it's some independent variable name, is defined as the n-1th order polynomial, so c1 times x to the n-1 plus c2 times x to the n-2 all the way down to cn x to the 0. Okay, and there's one more thing I have to tell you. These C1s, these subscripts, C1, C2, Cn, they are binary things. They are the same as these bits that we had up here. Which means that these sums, these add symbols, you can take them to mean bitwise XOR. You can take them as modulo 2 sums. Okay, so if we can define, if code word vector C maps to this polynomial, then we can also talk about shifting that code word by I places, and we get the x's stay the same, but the coefficients get shifted. So this would be then C1 x to the I-1, and at the end we have C sub I. Okay, where again the superscript I means the cyclic shift to the left by I spaces. Okay, I need a couple of intermediate results. Well, I need one intermediate result before we get to the big result with cyclic codes, and that is one little small claim here. Please interrupt me if you're not following any of this. the remainder between these two polynomials, so x to the I times c of x divided by x to the n plus 1 is one way to generate an ith shifted version of c of x. Okay, one more time here. I'm looking at a fraction on the left here, and the fraction on top has the code word polynomial c of x multiplied by x to the I. This is truly x to the I, not x with some shift, because there's no parentheses around the exponent there. So take x to the I multiplied by c of x, you'll get another polynomial. Divide that by the polynomial x to the n plus 1. You'll have a polynomial division problem, which then will have a remainder. And the claim is the remainder after this process is the same as shifting the original code polynomial by I. This is not at all obvious to me, but the proof is actually quite short, so let me run you through that. So what I'm going to do is I'm going to prove it for I equals 1, and because everything here is cyclic, you get to just turn the crank for 1 shifts, and you get I shifts. So we're going to let little I be 1, and then I'm just going to set up the fraction on the left-hand side. And we have, under the division sign, we have c1 x to the n. I'm going to write c of x times x plus c2 x to the n minus 1. And then all the way down to cn times x to the 1, and then 0 x to the zeros. Right, so what's important here is that we're multiplying by x to the 1. And we're going to divide that by x to the n plus 1. Oh, right. Everyone got their long division pants on? Sorry, I should have warned you. Long division can be traumatic, I know. How many times does x to the n go into c1 times x to the n? Well, you need c1 copies of it. Okay, so this is just like in elementary school, where I get c1 times x to the n, and then the only other term down here is going to be c1 x to the 0. And then now is where we diverge from elementary school long division. Because in elementary school, you would have put a minus there and carried on your merry way. But because we're doing bitwise XORs, because we're doing modulo 2 arithmetic, subtraction is the same as addition. Okay, so you can work that out for yourself, that 1 minus any bit minus any other bit is the same as that first bit XOR with the second bit, which is the same as the first bit mod 2 added to the second bit. Okay, so we can either do minus or we can do plus. They end up being the exact same thing. And what we get is this term and this term will cancel. And we're left with c2 x to the n minus 1 dot 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 all the way down cn x plus c1, which if you check is the 1 shift of our original polynomial. And this is indeed the remainder. Okay, so that's the quick proof of that, is to get a shift of I, and we talk about codes as polynomials. It's sufficient to multiply the original code word by x to the I, divide by x to the n plus 1, and take the remainder of that procedure. And that's one way to generate an I place circular shift. So in linear block codes, we had these generator matrices. So recall that we had the idea that we can take bits as row vectors and multiply them by matrices and get new row vectors. We called those matrices the generator matrix of the code. In thinking about these as polynomials, we have generator polynomials. So the definition of a generator polynomial call it little g of x, is simply a polynomial that when you multiply it by a data polynomial, you get a code polynomial. Is a polynomial such that d of x times g of x gets you c of x. Right? If you're comfortable with talking about data words and code words, then you're comfortable with thinking about strings of zeros and ones. Now, instead of thinking about commas in between them, thinking about each of those bits multiplying an x to the n, or an x to the n minus 1, or an x to the n minus 2. Okay. So let's take a quick aside, and we'll say that, because we're going to be all about degrees of polynomials. So the degree of a polynomial, just to remind you, is the highest power of that polynomial, highest power of x, if you like. So note that when we defined the code polynomial c of x, c itself is an n vector, right? There are n bits in every code word. But because we have the 0th power here, this is degree n minus 1. So all of our degrees are going to be 1 less than the lengths we've been using so far. Which means that if this guy is degree n minus 1, then the data polynomial would be degree k minus 1. And that also means that the generator polynomial must be degree n minus k. Because when I multiply polynomials, I add their degrees. Okay, this brings us to the big hurrah of today, and that is called the cyclic linear block code theorem. So I'll say it first so you can start copying it down before I take forever to write it down. But the statement of the theorem goes, if g of x has degree n minus k and is a factor of x to the n plus 1, those are the only two requirements. If your generator polynomial has degree n minus k and is a factor of x to the n plus 1, then g of x generates a cyclic code. Okay, so if the following are true, if g of x has degree n minus k and g of x is a factor, which means it divides into evenly, of x to the n plus 1, then we say g of x is guaranteed to generate an nk cyclic code. Then g of x generates a cyclic code. And this is pretty powerful because I think to find something that makes a cyclic code would be kind of tricky. I mean, remember what it's looking for? It means that it would be a polynomial of specific order that when you multiply by any of the polynomials of degree k minus 1, you will get a polynomial whose coefficients are cyclic permutations of other possible images of this transformation, which is like if you just picked a polynomial of degree n minus k at random, it would not do this, right? So this is a way to constrain ourselves to only look at generator polynomials that will actually give us cyclic codes at the end of the day. I have a proof for this, but I think I'll start it today, and then we will wrap it up. Oh, not on Wednesday. We actually haven't talked about this. Wednesday's a holiday, and so the next time I will see you all will be Friday, which actually suggests that it's kind of a crapshoot for me to start this proof today. But I think it is an interesting proof, and it's got some content in it that will become useful later on. So I don't really want to skip it. So we'll end this with proof on Friday. Okay, so use the extra 2 minutes I'm giving you, and email me asking to get into 526. That's your assignment. Okay, thanks everyone.